In 1908, the Guinness Brewery in Dublin had a serious quality control problem. They employed a chemist named William Sealy Gosset to guarantee that every batch of their famous stout tasted exactly the same. But Gosset was stuck. To test the chemical makeup of the barley and the beer, he had to destroy it. If he analyzed a large enough sample to get mathematically certain results, he was actively ruining the product. He could only test a tiny fraction of a batch, or Guinness would have no beer left to sell. That created a massive mathematical hurdle. The standard statistical tool of the day, the z-test, required you to know the exact variance of the entire population of data. For Gosset, that meant knowing the precise chemical measurements of every single drop of beer in the factory, an impossible metric. If you take a tiny sample of barley and run it through a z-test anyway, the math assumes you have perfect information. It gives you a confident result that might be completely wrong. Rely on that error, and you risk letting thousands of inconsistent barrels be shipped out to pubs. Since the company forbade employees from publishing research, Gosset went rogue. He invented a new mathematical model specifically designed to account for the guesswork of small samples, and he snuck his findings into an academic journal under the pseudonym Student. Gosset recognized that real-world business problems rarely hand you perfect, infinite data. If you want to make reliable decisions based on small fractions of information, you need a mathematical tool that explicitly accounts for your own ignorance. This is a chart showing the standard normal distribution, or the z-curve. It is symmetric, precise, and represents an ideal scenario where every piece of data in a population is known and certain. But estimating your standard deviation from a tiny sample, like taking just 5 drops from a massive vat of beer, removes that certainty. To account for that layer of doubt, Gosset's math physically alters the shape of the curve. The center drops and the edges spread out. These heavier, fatter tails are the defining feature of Student's t-distribution. They mathematically reflect the fact that when you're working with limited data, extreme, unexpected values are far more likely to occur than a standard normal curve would predict. The exact shape of this t-distribution is controlled by a single parameter, degrees of freedom. This metric is directly tied to your sample size. The smaller your sample, the lower your degrees of freedom, and the fatter those tails get to absorb the extra risk of error. But as you collect more data, that uncertainty shrinks. Watch what happens as the sample size increases past 30. The t-distribution tightens up and converges perfectly back into the precise shape of the standard normal curve. The t-test functions as a flexible small sample correction, ensuring that inferences remain statistically valid even when researchers are forced to work with limited data. Today, Gosset's math is the standard logic test used across almost every industry to determine whether an observed difference is mathematically real or simply a random fluke. This diagram illustrates a one-sample t-test. You use this when comparing a single group against a fixed benchmark. For example, if their claim actually holds up. Here, the chart displays an independent t-test. This compares the averages of 2 entirely separate groups, like transaction values at store A versus store B. Because real-world groups rarely have the exact same amount of internal variation, researchers default to a calculation called Welch's t-test, which handles unequal spreads without distorting the overall error rates. The third variation is the paired t-test. Here, we're tracking the exact same subjects measured twice, like timing individual employees before and after a training program. Connecting these data points isolates the actual effect of the training by filtering out the baseline differences between individual people. For any of these tests, you have to decide between a one-tailed and two-tailed approach. A two-tailed test looks for any difference at all, higher or lower. A one-tailed test specifically checks if a value moved in a single direction. There is a strict rule here. You must choose your direction before looking at the data. Switching your test afterward just to manufacture a statistically significant result is a mathematical foul known as p-hacking. While these 3 tests apply to distinct setups, their ultimate objective is identical, separating a genuine, actionable business effect from random statistical noise. Getting a passing grade on a t-test, a low p-value, answers exactly one question. Mathematically, does a difference exist? It tells you nothing about whether that difference is large enough to matter in the real world. This diagram charts an essential companion metric called Cohen's d, which measures effect size. While the t-test detects a real effect, Cohen's d calculates the actual magnitude. A score around 0.2 indicates a small difference. Moving up to 0.5 points to a medium, noticeable change, and 0.8 or higher highlights a large impact. Keep in mind that a t-test relies on a few core assumptions. If your individual data points actually influence one another, or if you apply the test to a small, heavily skewed sample with massive outliers, the math breaks down and the results become unreliable. When William Sealy Gosset first sat down to solve his quality control problem, he was dealing with physical stakes. He needed a way to confidently ship good beer to actual people, using the smallest amount of information possible. Because of Gosset's work, modern researchers don't need infinite data to act. With the right mathematical curve, a handful of observations can provide enough evidence to justify a major decision.